A ball is thrown horizontally from the top of a building at 27.6 meters per second and lands 44.2 meters from the base of the building. How tall is the building? So what we know is that horizontally, the ball travels 44.2 meters. The horizontal velocity is 27.6 meters per second. Horizontally, the acceleration is 0. Gravity only works vertically. So we can simply work from distance is vt. Well, in this case, we go 44.2 meters at 27.6 meters per second. So it's only going to take about 1.60 seconds for the ball to travel the 44.2 meters. Vertically, we know that since it's thrown perfectly horizontally, we do not know how far it's traveling. We do know that the initial vertical is 0 because it is thrown perfectly horizontally. The acceleration is a negative 9.81 meters per second squared because we do have gravity to contend with. Now, since this is not doing a full parabolic path, but only doing half of it, our time is the 1.60 seconds. That's our total air time. Displacement is 1/2 at squared plus vit. Our initial vertical speed is 0, so that term is gone. 1/2 and negative 9.81 and 1.60 squared. So what we know is, in fact, this is an approximately 12.6 meter tall building. And again, we have 3 significant digits, so we've got 3 significant digits here. You may have actually heard the term relativity. The idea of what we call relativity is sometimes referred to as Galilean relativity and Einsteinian relativity. Now, the Galilean one is the pretty straightforward one in that it's simply going to be that the total motion of an object is the vector sum of the independent motions, and that's a misspelling right there. That should say independent, not independent, motion of the object and the motion of the frame of reference. I sometimes make the analogy of if you're riding in the back of the truck throwing things over the cab, the speed of the object is going to be the speed of the truck plus the speed that you're throwing it. Whereas if you're in the back of the truck and throwing stuff out the tailgate, then the speed is going to be the speed that you throw it minus the speed of the truck. Now, when I refer to the Newton's laws of motion basics, these are the kinds of things that I'm talking about. They're just the very, very surface level. We'll get into it more in the second unit, but the very surface level of Newton's laws of motion. First, that the resistance to change that we refer to as inertia is measured as inertial mass. The change in momentum is proportional to a change in motion, and momentum is conserved. So resistance to a change, inertia, is measured as inertial mass. This usage of inertia as a resistance to change, with Newton's laws, it is resistance to change in motion, but in fact, you'll sometimes see that now in common usage when it's concerning organizations and other things that are reluctant to change or slow to change. But in fact, it's a matter of how much. And it just says that mass basically is what is measuring this inertia. So for us, we're talking about it in terms of kilograms. What that basically implies is there is more resistance to change in a 100 kilogram object than in a 50 kilogram object. The change in momentum is proportional to the change in motion. The short form of this basically says F equals ma, and this is the short form of Newton's second law. Okay, change in momentum. So we have this thing called momentum that turns out to be P equals mv. A change in momentum would be P over T, which is in fact what you would get if you divided both of these by time. So F equals ma, which is equal to P over T, is essentially what you're looking at for Newton's second law. Newton's third law, we'll talk about in just a second. What force is needed to accelerate a small child across a well-waxed floor, if we ignore friction, at 2.25 meters per second squared if she has a mass of 17.3 kilograms? So in other words, basically what we have is we have a small child sliding on a waxed floor. F equals ma. Mass 17.3. Acceleration 2.25. The total force needed is 38.9. The units, kilogram, meter per second squared, or more commonly, this is a derived unit that we call a Newton. No big shock as to where the name came from on this one. What is the average force needed to accelerate a 7.21 gram pellet from an air rifle with a barrel length of 3/4 of a meter from rest to 100 meters per second? Okay, so a change in velocity is equal to 100 meters per second. Our delta x is 0.75 meters. So what is our acceleration? How are we going to find our acceleration? We don't know our time. But we do know that it ended up at 100 meters per second. It started at rest. We don't know our acceleration, but we know it happened in 3/4 of a meter. So from this, we can find our acceleration as a lovely 6,666.7 meters per second squared. Now be careful because this mass is in terms of grams and we need it in kilograms. So 7.21 grams. All right, so 1,000 grams per kilogram, which is equal to 7.21 times 10 to the minus third kilograms. If we're looking for a force, we can use the short form of Newton's second law, so that the average force is simply going to be this 7.21 times 10 to the minus third kilograms times a 6,666.7 meters per second squared, which is going to give us 48.1 newtons. Now, to give you some idea of about how big a newton is, think about a kilogram. A kilogram would have a mass of approximately 9.8 or about 10 newtons. Okay, a kilogram is about 2.2 pounds. So roughly speaking, somewhere between 4.5 and 5 pounds is 1 newton. So this is going to give you somewhere on the order of about 10 pounds of force. Newton's third law basically says that momentum is